Hi everyone. In this lecture we're going to learn a systematic method for solving linear systems. So let's start by looking at an example. Here's a system of equations in 3 variables, and suppose we want to solve it. So that means we want to find values of x1, x2, x3 such that all 3 of these equations are true. So how do we go about doing that? Well, the big idea of algebra is that there are moves that you can do that can simplify the equations. And then when you simplify the equations enough, you might eventually get to the point where you can see what the solution is. This is basically what you've done in high school algebra when you've been solving equations. You have some moves, you might move terms from one side to another, you might multiply both sides of the equation by something or divide both sides of the equation by something. And the idea is that every single one of those moves doesn't change what the solution is to the equation. And so you can take a complicated looking equation and simplify it using those moves into a simple equation where you can see what the answer is immediately. So we're going to do that here, and the first question is, what moves can we do? So here's one move you can do. You can take any of the equations and you can multiply or divide it by a non-zero constant. This is something that you're comfortable with doing. You used to do this in high school algebra, solving like 3x plus 2 is equal to 15 or whatever. You can multiply both sides of the equation by a number. You can divide both sides of the equation by a number. And of course, if you multiply by 0, that's problematic because that'll just make the equation 0 equals 0, which sort of erases the equation effectively. And of course, you can't divide by 0 either. But as long as you're working with non-zero constants, you can multiply or divide by anything. So another move we can do is to reorder the equations. Because really the order of the equations doesn't matter at all, right? We want to solve all 3 equations simultaneously. It doesn't matter what order we write them in. This might even feel like it's not a real move, like what are we doing? But it's going to turn out that this is useful later on. Now a third move we can do is that we can add or subtract a multiple of any equation to or from any other equation. This one you might need to spend a little bit of time thinking about. The idea is that if you have 2 equations that are supposed to be true when we solve them, then you can take 2 things that are equal, and then you can take 2 other things that are equal, and you can subtract a multiple of the one set of things from the other set of things, and you'll still have things that are equal. Okay, just think about it a little bit, but this works. This is actually the move that we were doing when we were eliminating variables in the previous video. Now what we're going to find is that these 3 moves are enough to provide an algorithm for solving any linear system, any number of variables. But before we describe the algorithm in general, let's just see how it works in this example. And before we even do that, I want to introduce some notation that's useful to use. This is called matrix notation. So this is what the system looks like in matrix notation. You can see that what I've done here is basically I'm not writing out x1, x2, x3 anymore. I'm just writing out the coefficients. So because it's 1 times x1 plus 4 times x2 plus 2 times x3, there's a 1, 4, 2. And then the minus 2 represents the right-hand side of the equation. And you can see that there's a little vertical line there that divides the left side of the equation from the right side of the equation. For the time being, you should just think of matrix notation as being a shorthand, as a way of describing the system without having to write out all of the x1, x2, x3, and the plus signs and so on. It just abbreviates the notation a little bit. Later on, we'll see that there's something more substantial going on, and that there's a sense in which you can think of a matrix as being a real thing in and of itself. But for now, just think of it as shorthand notation. And so now, every row of the matrix represents one of the equations in the system. And so if we look back at this list of moves that we made, the moves describe manipulations that you can do to the equations. We can now interpret those moves as being manipulations that you can do to rows of the matrix. And then because these moves play a very special role in the subject, they have a fancy name, elementary row operations. And this matrix that we're looking at here is referred to as the augmented matrix of the system. The word augmented refers to the fact that it has both sides of the equation. There are going to be some points later on where we're only going to focus on the left side of the equation and ignore what's on the right. And when we do that, then it's going to be just called a matrix. Okay, so what we're going to do now is we're going to start with this augmented matrix, and we're going to perform elementary row operations to try to simplify the matrix into something where we can see the solutions of the system. Let's do that. So the first thing I'm going to observe is that there's a 1 here in the first entry of the first row, which I can use to eliminate the non-zero entries in the same column as the 1. The role that this 1 is playing is important enough that it has a special name, and we call it a pivot. So to use the pivot, I'm going to subtract 2 times row 1 from row 2. And when I do this, row 1 stays the same, and row 2 changes. So the new row 2 is 2 minus 2 is 0, 9 minus 8 is 1, 1 minus 4 is minus 3, and then minus 2 minus minus 4 is 2. You got to be careful with the signs because here I'm subtracting a negative. And the key point here, the reason we did this move, is that it created this 0 in the first column. This way the pivot becomes the only non-zero entry in that first column. You'll notice that we didn't have to do anything to the third row because it already had that 0 there. Otherwise, we would have subtracted some multiple of the first row from the third row as well. Okay, so what should we do next? I think at this point it sort of helps to imagine that we're sort of done with the first column, like we've done as much work as we can do on that first column. And because that first column sort of involves the first row, we can sort of ignore the first row for the time being and just focus on the part that's below and to the right of the pivot. And when we look at that part, we can think of that 1 in the second row as being a new pivot. And then we can use that to eliminate the 1 that's in the third row below it. So to do that, we'll subtract row 2 from row 3. And when we do that, row 1 stays the same, row 2 stays the same, row 3 is the only row that changes, and it becomes 0, 0, 8, minus 6. Again, be careful about the negatives. It's 8 because you're subtracting minus 3 from 5, so that becomes 8. And then it's minus 6 because you're subtracting 2 from minus 4. Now at this point, the matrix is in a special form that's called echelon form. And what it means to be an echelon form is that the first non-zero entry of each row is to the right of the first non-zero entry above it. If we look at this particular example, the first non-zero entry in each row are here, and you can see that the first non-zero entry in the second row is to the right of the one above it, and the first non-zero entry in the third row is to the right of the one above it. They don't have to be immediately to the right, they could be farther to the right than just one step, but they have to be to the right. And these first non-zero entries in each row are what we call the pivots. And there's one more technical thing we need to add in the definition of echelon form, and that's that sometimes when you do these row operations, you can end up with a row of all zeros. And of course, if you have a row of all zeros, then there is no first non-zero entry, and so we need to specify that those rows of all zeros are at the bottom. Now, once you've got a matrix in echelon form, you're already in pretty good shape, and you could solve the system fairly easily from here. In this example, if I turn this matrix back into a system of equations, this is what I get. And you see that you can now sort of work your way backwards. You can use that last equation to solve for x3, substitute that in to solve for x2, substitute those in to solve for x1, and you're good. This technique is called back solving. From the third equation, you have x3 is equal to minus 6 over 8, which is minus 3/4. And then we would substitute that into the second equation. And that would give you x2 minus 3 times parentheses minus 3/4 is equal to 2, which you can solve for x2 and get x2 is equal to minus 1/4. And then you can substitute both of those things into the first equation to get this equation that only has x1 in it, so you can solve for x1 and get x1 equals 1/2. And so that's it. We've solved the equation. And I'll ask you right now to just stop for a second, write down these numbers that we got as the answers, go back to the original system of equations that we started with, and check that if you actually plug in these numbers for x1, x2, and x3, it works. All three of the equations are actually true. So that tells us that it's a solution. And this is something that in general you should do. Check that your answer is correct. You can always do that just by plugging them in and seeing if it works. Now at this point you might say that the row operations that we did on the matrix helped, for sure, but we still had to do some work, this back solving, in order to solve the system of equations. Could we have done that work in the matrix? And the answer is yes. There are more steps that we could have done. We didn't have to stop at echelon form. We could have done more. So one thing we could do is we could multiply or divide the different rows in order to make the pivots equal to 1. Now in the first and second rows, the pivots are already equal to 1, so we're good with those. But the third row has an 8 for its pivot. We can divide by 8 in order to make that pivot equal to 1. And now you'll notice that up until this point, we've sort of been working our way down from the top. Like we started with the first row, and we used the pivot in the first row to eliminate the terms below it. And then we used the pivot in the second row to eliminate the term below it. But now we can actually work our way backwards from the bottom and use the pivots to eliminate the terms above them. So if I subtract 2 times row 3 from row 1 and add 3 times row 3 to row 2, it'll eliminate the terms that are above that pivot in the third column. So when you do that, this is what you get. Again, be careful with the signs. There's a lot of subtracting negatives that can happen when you do this stuff. And then, finally, we can use the pivot that's in the second column to eliminate the 4 that's above it. So to do that, we would subtract 4 times row 2 from row 1. And this is what you get. Note that subtracting 4 times minus 1/4 is the same thing as adding 1, and so that turned the minus 1/2 into a plus 1/2. And now when we turn the augmented matrix back into a system of equations, the equations are the solutions. x1 is equal to 1/2, x2 is equal to minus 1/4, and x3 is minus 3/4. And so we didn't have to do any more work. The solution was already there. So these additional steps that we've done beyond echelon form put the augmented matrix in what's called reduced echelon form, which is sometimes abbreviated as RREF. So what it means to be in reduced echelon form are that you have all of the conditions for echelon form, which means that the first non-zero entry of each row is to the right of the first non-zero entry above it, and that if there are rows of all zeros, they're at the bottom. But in addition to that, we require that all of these first non-zero entries, which are called the pivots, are equal to 1, and each pivot is the only non-zero entry in its column. And so if you look at the matrix that we ended up with at the end of this process, it satisfies these conditions. It's in echelon form, all of the pivots are equal to 1, and if you look at every column with a pivot, those pivots are the only non-zero entries in those columns. You'll notice that there is this additional column on the right, and so that column is kind of a free-for-all. Anything can happen there. So one thing that's important to know is that there is an algorithm that you can systematically use to turn any matrix into a reduced echelon form matrix, which then basically solves the system of equations. And this algorithm is called Gauss-Jordan elimination. And I should point out that the value of an algorithm is that it's not just something that you can do, it's something that you can program a computer to do. And just so you know, I'm going to ask you to do it a few times by yourself, by hand, just to demonstrate that you understand how the algorithm works. But after you've done that, it's going to be totally okay to just use a computer to do this, and it's going to save us a lot of time. So here is roughly how Gauss-Jordan elimination works. First, you start by working from top to bottom, identifying the pivots in each row, and then eliminating the non-zero entries below those pivots. In this process, you might actually encounter a row of all zeros, and when that happens, you'll have to swap some rows in order to move that row to the bottom. So that's where you use the row swap move. And at the end of this step, you will have the matrix in echelon form. And so then it's just a matter of putting it into reduced echelon form. And so to do that, you would multiply or divide in each row to make the pivots 1. And I'll point out that this is something that you could actually do in conjunction with step 1, or you could even do it at the end. This is something that could really be done at any point in the process. And then you would work from bottom to top, eliminating the non-zero entries above the pivots. And at the end of this step, you will have the matrix in reduced echelon form. Now this algorithm, it's pretty cool. First of all, just being an algorithm, it's systematic. You can program a computer to do it. That saves us a lot of time. We don't have to mess around with all these calculations. Even better, it's a pretty efficient algorithm. If you sort of think through the number of calculations that you have to do to make this work, if it's a system of m equations and n variables, the number of calculations is something like 3 times m times n. So, for example, if you had a system of 1,000 equations and 1,000 variables, that sounds like a lot of work, but it's really just about 3 million calculations, which a computer can do in a split second. So it's efficient even for systems that have many equations and variables. And then finally, and this is the thing that we're going to spend most of our time on, if we want to figure out what are all the different things that can happen when you solve systems of linear equations, we don't have to look at all systems. We can just look at the ones that are in reduced echelon form because we know that every system can be put into reduced echelon form. So basically we get to assume that that step has already been done for us. So there's a fancy term for this that mathematicians use, which is without loss of generality. So what that means is, since every system can be put into reduced echelon form, we don't actually lose generality by assuming that a system is in reduced echelon form. So we get to do that when we're analyzing the behavior of systems. Okay, so far I've only shown you one example. I should do at least one more. Here is a system of equations. So here's a system of equations. And if you rewrite this as an augmented matrix, you get this. And now we can start working our way from top to bottom, following the Gauss-Jordan elimination method, and identify what the pivots are. So that 1 in the first row is going to be a pivot, and we're actually lucky in this case. There's already zeros below it, so we don't have to do any work to eliminate the entries that are below that 1. So we can go ahead and move on to the next pivot, which is this 2 in the second row. And now we need to use that 2 to eliminate the 2 that's below it. So to do that, we'll subtract row 2 from row 3. And now this is what you get. And now we can identify the pivot that's in the third row. And we can see that this matrix is in echelon form. Each pivot is to the right of the pivots that are above it. So now the next step of the Gauss-Jordan elimination method is to make the pivots 1. So the pivot in the first row is already a 1. For the second row, we need to divide by 2 to make that pivot a 1. Okay, so we can do that. And now all 3 of the pivots are equal to 1. Now we move on to the third step of Gauss-Jordan elimination, which is to work backwards from the bottom to the top and eliminate the entries that are above the pivots. So first we want to get rid of the 2 that's above the pivot in the third row. And to do that, we'll subtract 2 times row 3 from row 1. And this is what we get. And now we want to get rid of the 2 that's above the pivot in the second row. And to do that, we'll subtract 2 times row 2 from row 1. And then this is what you get. And this is in reduced echelon form. If you look at these pivots, they are all equal to 1, and each of them is the only non-zero entry in its respective column. Okay, so here's the reduced echelon form of the matrix, and if we turn it into a system of equations again, we get this system of equations, which doesn't look quite as nice as the ones that we've seen before. It doesn't look like it's solved, maybe, but it actually is. And to see that, let me rewrite it in a slightly different way. So when it's written like this, you can see that x1 is equal to x3, x2 is 1 minus 2x3, x4 is equal to 1. We have an equation that tells us what x1 is, we have an equation that tells us what x2 is, and we have an equation that tells us what x4 is. X3 in this expression can be anything. And this is actually part of the solution. The idea is that you can choose different values of x3 and you'll get different solutions. This is a case where the solution is not unique. So the terminology is that x3 is called a free variable. And then once you decide what x3 is, then that automatically tells you what the other variables are. And to emphasize this, it's common to set the free variables to be equal to some other variable that looks more like a parameter. So in this case, I set x3 to be equal to t, and then plug that in for the other equations. So now I've got x1 is equal to t, x2 is equal to 1 minus 2t, x3 is equal to t, and x4 is equal to 1. And together this solves for all of the variables as a function of this parameter t. And so you can imagine that t can be anything, and that would give you all the different solutions. And you could even think of this as a description of a parametric curve. And in this case, it's actually a line in four-dimensional space that describes the set of all solutions. Now you might ask, why did we set x3 to be the free variable as opposed to one of the other variables? You could potentially have set one of the other variables to be the free variable, but there is one particular choice that comes from the Gauss-Jordan elimination algorithm. And you can see that by looking at where the pivots are in the matrix. The first, second, and fourth columns of the matrix had pivots, and those are the columns that correspond to the variables x1, x2, and x4. The third column did not have a pivot, and that's the column that corresponds to the variable x3. Because of the rules for how reduced echelon matrices are defined, you'll always be able to solve for the pivot variables in terms of the non-pivot variables. And so that means that you can set the non-pivot variables to be free variables and solve for the pivot variables in terms of those free variables. And so that's exactly what we did here. That's why we set x3 to be the free variable. Okay, we'll talk about all this more in the next lecture, but this should get you a start. You now know what reduced echelon form is, you know what echelon form is, and you know how to do these row operations to do the Gauss-Jordan elimination to get to those, and you know how to use those to solve systems of equations. Bye.